and welcome to Enough with the Science. I'm Joe.
And I am Senan, and this week we have an out of the world episode for you.
We're heading deep, well, maybe not deep, maybe shallow space we're going to this week.
We're going to go deep up into space.
But space is in the news this week. Yes, we have that rocket launch with that famous singer, Katy. Who was her name?
Katy Perry. Yeah.
Katy Perry.
Now
yes.
people know when we recorded this.
Now, that could have been this week or last week or last month. We're terrible with time.
Mind you, which one of Katy Perry's flights are we talking about is the question.
In the future, they will look back and they will never be able to date this episode. It'll be timeless.
Anyway, Joe, I have a bit of a confession to make.
Okay. No, here we go.
This
I like you, but not in that way.
This episode is complete and utter self-indulgence for me because I'm a bit of a rocket nerd.
So it is actually rocket science.
Yeah, we are talking this week about rockets, what they are, why they work the way they do, why we need to use them, all that good stuff.
Do I get to probe? Do I get to probe and not a space probe, but
an alien probe?
Well, just to try and figure out what drives Senan Mahan. Like what is it about rockets? When did you become a rocket nut?
I suppose it's a combination of factors, isn't it? I mean, first it's the sheer amount of physical power that's on display when a rocket engine is running. That's just awesome. That there's nothing else we do that concentrates so much power. You just love
burning fuel. That's what you just love, like burning tons and tons.
Then, of course, there's that whole business of the excitement of maybe the human race expanding out into space. Because, like, let's face it, if we could take a little analogy, if the Earth that we all live on is like one grain of sand, well, then the rest of the universe is far more than all the other grains of sand on all the beaches everywhere on Earth. In fact, if you were to take all the grains of sand on Earth and all the grains of sand on Mars, you still wouldn't have a suitable analogy for the size of the rest of the universe. So it's a big space out there, and it's kind of exciting to think that we have these machines that might one day let us get out there.
Imperialist expansion. You have notions of imperialist expansionism.
Try saying that after.
I know, yeah. I can't even say it now.
So anyway, I suppose we start off with the basics.
We always do.
What is a rocket?
Mm-hmm.
So essentially, if you throw stuff out the back at high speed,
You're going to be more specific now. Come on.
We're getting there. We're going to start at the absolute basics.
There's a machine. There's a machine of some sort.
Yeah. No, but if you throw stuff out the back of a thing at high speed, thanks to Isaac Newton and his third law, you get an equal and opposite reaction that pushes you forward. So that's essentially what a rocket is doing. It's throwing stuff, in this case hot gas, at very high speed out the back, and lots of it in a very short period of time, and that pushes you forward with the opposite reaction.
And is there anything in nature that somebody looked at and went, ooh, that's how that works, and then they decided to copy it?
It's funny you should say that. I mean, there are underwater creatures like squid and octopus have an escape mechanism, and actually scallops do it too, where they literally squirt a jet of water if they're under threat out of some kind of squirty thing in their body. And
there's a word for it. I'm sure there's a word for it.
And they can suddenly dart off in the opposite direction to get away from a predator. So yeah, I mean there's some precedent for it in the natural world. Now, the interesting thing about rockets, of course, is that we're using them to go up into space, and gravity pulls everything back down to the Earth. And to get into space, you need to throw an awful lot of stuff out the back awfully quickly to get that forward motion from Mr. Newton. And rockets are really good at that. That's kind of why we're using them.
And so what initially fueled human innovation in rockets? See, fueled. Look at that.
Well, of course, now that you've mentioned fuel, which is going to form a large part of this discussion, the rocket fuels have got to be highly potent. They've got to be able to produce a lot of thrust, and we'll be talking in extensive, nauseating detail later about rocket fuel and what it is and why we use it.
All innovations. Who was at it first? Who were?
Yeah, so
the innovators.
The earliest records I think that we have go back to the Chinese in the 10th century. They had these fire arrows, so there were tubes full of gunpowder that they could literally launch. I guess there were probably bamboo poles full of gunpowder.
Right.
And they'd light one end of it, and the thing would take off like the clappers and land on your enemy and set his stuff on fire.
Like just for fireworks. It was.
Oh well, probably that as well. But yeah, no, I think they used them in battle as well. And then the Mongols, who of course had battles with the Chinese in the 13th century, they learnt about those techniques and they started using the Mongol Empire spread all over the place.
So Mongols and Chinese were firing rockets at each other, the guts of 800 years ago.
Yeah, well, pretty basic ones. Yeah. But yeah. So then if we move a bit forward into the modern age, in the United States, around 1926, a guy called Robert Goddard, a scientist, he launched the first known liquid fuel rocket. Now, there's all kinds of reasons why why you want to use liquid fuels in your rockets, but his was the first successful one that we know of, and it was petrol and liquid oxygen that he used. And it lifted up only for a paltry 41 feet, but at least it did get into the air and didn't kill him.
That's always good when you're doing experiments.
Because the history, unfortunately, is littered with examples of experimental rockets that did kill people.
Right.
But then, coming a little bit further after him, the Soviet military in the 30s, in the 1930s, they experimented with rockets, and they actually successfully shot down a couple of planes with their experimental rockets.
So this is only 10 years after the first person put one up, we were shooting down planes with it.
Yeah, well, I mean, I don't think they were reliably shooting down every plane they could try. They tried to shoot down, but they did hit a couple of them.
They actually probably weren't trying to shoot down the planes.
Yeah.
they just randomly,
well have been the case.
oh.
Yeah. But those are all... none of those rockets really looked anything like the kind of rocket that we think of today when we think of a space rocket. So to get something that looks like a modern rocket, we've got to move into World War II, and regrettably it was the Nazis who came up with the next big innovation, their V2 missile, which was used to bomb Britain. It looked like a modern rocket. It was a pretty big thing. It was 14 meters tall.
Yeah.
And again, liquid fuels, ethanol, which is pure alcohol, and cryogenic oxygen. I'll come back to what the cryogenic bit means in a while.
Oh, yes, you will.
But that was, even though it didn't go fast enough to actually get away from the Earth or even to go into orbit, it did get into space briefly because it was launched on what's known as a high arc ballistic trajectory. So essentially it went up at a high angle, almost straight up. Well, not quite, because if you put it straight up, it'll come back down on top of you. But only a very slight angle, so almost straight up. And it went into a very high arc, out into space beyond the atmosphere. And then the engine cut off and it began falling back down. And they had, because of the way they carefully aimed it, it would come down in Britain somewhere, that they were aiming it at.
I wonder, is there like someone forgotten in the history of rocketry who discovered that you shouldn't point a rocket directly up?
Yeah, perhaps, and forgotten fairly quickly, I'd say. Like that. So that was, as far as we know, the first man-made object that went into space, even though it was only in space briefly, and it was used for very dark purposes. And I mean,
so we use rockets to fire these things up into space, but now we use jet engines to sort of propel us up into the sky. Why not use jet engines for rockets?
Yeah, and it's a very good question, because of course jet engines are massively reliable. They're used, like right now as we're speaking, there are thousands of planes in the air around the world using jet engines. They're very fuel efficient, and they get us places very fast. But the interesting thing is, right, so we need to talk about what is combustion, which is essentially what's going on, or burning, for a simple word for combustion.
Good, let's use simple words. I like simple words.
So burning is essentially a chemical reaction usually between oxygen and some other fuel. Now the reason I say usually between oxygen is because technically it's an oxidizer. There are other chemicals like fluorine and compounds of oxygen and stuff that you can use as an oxidizer in a burning reaction. It doesn't always have to be oxygen, but it's usually oxygen that you're using. And essentially oxygen is one of those chemicals that wants to react with absolutely everything you bring it into contact with. And some things you bring it into contact with, it reacts so violently with them, those things we call fuel, that it burns, produces this massive amount of heat and massive amount of expanding hot gas when you burn. So that's essentially what's going on in both a jet engine and a rocket engine. The difference is, of course, the jets don't carry their own oxidizer. They don't have a tank of oxygen. Right. In the jet, so they're relying on the oxygen in the air that we're breathing so they're carrying a tank full of kerosene or something that's very like kerosene, but they're relying, that's the fuel part, but the oxygen part is coming from the atmosphere. So there's a couple of problems with that if you want to use it if you want to use it for launching a rocket. One is like once you go above an altitude of about 30 kilometers, the density of the air in our atmosphere has reduced so much that there just isn't enough oxygen there to support the jet engine, to run the jet engine.
Right.
That's the first problem. And obviously, most rockets we know go up into space and there's no oxygen at all up there, so the jet engine couldn't.
That would be a problem.
Couldn't run up there.
Yeah.
But the other thing is the amount of thrust you get from a jet engine. In other words, how much stuff it throws out the back, to go back to Mr. Newton from earlier on, is not really enough to launch into space. A rocket engine, by virtue of the fact that it's using really energy dense fuels and liquid oxygen, which is much denser than and more reactive than gaseous oxygen that's in the atmosphere, you get just much higher thrust out of a rocket. So that's kind of why we're using rockets to get into space instead of jets. Now, having said that, it's funny you should ask. There has been some hybrid approaches. Some companies have experimented with putting a smallish rocket under the wing of an airplane, flying that airplane up to nearly 30 kilometers above the ground to give the rocket a head start, as it were, and then launching the rocket from underneath the wing of the plane. They're having making it economically viable. You see, it's going to have to be a small rocket. Because planes can't carry great big heavy rockets, so that means whatever kind of a payload you're putting into space is going to be small too. And you mightn't be able to get it. You might only be able to get it into a low orbit because you can't put enough fuel on the rocket because it would make it too heavy, etc., etc. So it's not met with huge amount of success. But it's people have tried it. Yeah.
So like these are lightweight rockets. Essentially.
Yeah, lightweight rockets. Yeah.
But non-lightweight rockets, they certainly aren't lightweights when it comes to drinking fuel. A bit like you drinking, your drinking habits.
I know. I've gotten over that now. I'm on the wagon, or nearly. I'm certainly got one finger on the wagon anyway.
I've seen the wagon. I've seen the wagon when it passes.
So. I suppose, as I mentioned earlier, we need to talk about rocket fuel because it's a big part of the rocket story. So you need fuel that's to get a useful amount of payload into orbit. A satellite of a reasonable size or a capsule with a couple of astronauts in it. You actually need an awful lot of power, an awful lot of energy to overcome the Earth's gravity to get up to sufficient speed to actually stay up there. So that's why we need these really energy dense fuels to give the rocket enough power to actually achieve its goal of getting up into orbit or whatever. Because remember, it's got to lift the weight of the fuel as well. And for most rockets, just before they take off, about 70% of the entire weight of the vehicle is fuel. So,
right.
Well, fuel and oxidizer.
Right.
So, I mean, all that has to be lifted as well, at least in the early stages. Obviously, as time goes along, it's burning it and the weight of the fuel is reducing. But most rockets are using what's called cryogenic liquefied gas. So the oxygen in practically every case is cryogenic liquefied, and the other fuels like methane or hydrogen would also be cryogenic liquefied. Now, what does that mean?
Thank God.
Well,
I was just smiling and nodding there. I was going, yeah, cryogenic liquefied. I know what that means.
Cryogenic essentially means really cold. That's
right.
That's what it means. And the thing is, right, these at room temperature, things like hydrogen or methane or other gases that we might use as a rocket fuel, say propane or whatever, they want to be a gas at room temperature. So in order to persuade them to be a liquid, which concentrates them and gives us more energy, they'll burn more vigorously if we burn them from their liquid form versus their gas form. We actually have to make them cold. That's how you persuade them to go from becoming a gas to a liquid.
I like that description. You persuade them. Psst, come here. Yeah, we don't need you as a gas. We need you as a liquid.
Yeah. Take off your coat there. You're too warm.
Yeah.
So, like, if you think of it in terms of steam and water, water, as it happens, is liquid at room temperature. But if you raise its temperature above 100 degrees Celsius, it becomes steam and it turns into a gas. So it's the same thing in reverse going on with these. We just have to lower the temperature. But we're talking about really seriously cold here. Like liquid oxygen, the temperature of it has to be maintained around minus 185 degrees Celsius. And, it's similar kind of temperature for the cryogenic fuels.
Right. That's cold. That's colder.
That's pretty cold.
That's colder than winter.
In a minute, we'll talk about what the challenges are to do with dealing with that kind of cold fuel.
Yeah.
But we might as well talk about some of the other fuels. There is also sometimes solid fuel rockets. One of the most famous ones, of course, was the space shuttle, the NASA space shuttle. It had
Turf. Coal,
turf.
They're solid fuels.
Potentially, I'm not sure if they're energy dense enough or if they'll burn fast enough for our purposes. The space shuttle had a mixture, actually. It had two strap-on boosters on the side that were made of solid fuels, and then the three engines in the middle that were actually part of the vehicle itself were used liquid fuels. So it was a mixture. But you're talking about pretty exotic chemicals to make solid fuel rockets, and they're extremely powerful. Like the space shuttle crews used to report that as soon as the solid rocket boosters powered up when they were launching, the shuddering that went through the vehicle was just shocking. Like the force of them was incredible. Also, they have no off switch. Once you turn on a solid rocket booster, that's it. It's on until all the fuel is gone.
Right. So you don't want to change your mind. Oh, I've got my keys.
Yeah. But there's much simpler engineering, generally speaking, involved, because there's no fuel pumps or pipes or valves involved. It's literally, if you imagine, it's like a hollow candle. So they just set fire to the hole in the middle of the candle, and it burns from the inside out. So you're actually burning in the fuel tank, as it were. There isn't like a separate combustion chamber. And then getting even more exotic. Actually, I should probably talk about briefly the first space shuttle disaster. People might remember that there was two space shuttle disasters separated by many years. But the first one was caused by a problem in the solid rocket boosters. They launched the vehicle at a much colder, it was frosty weather, much colder air temperature than they normally would. And the solid rocket boosters were made in sections, in cylindrical sections, and they were joined together with little rubber O-rings to seal the outside of them so that the combustion would stay inside. And,
right.
But the cold weather, the frosty weather, made those O-rings brittle, and they didn't seal. And so the combustion was able to leak out the side of the rocket and burn the vehicle. So, yeah.
Oh, right. I'm sure somebody must have got in trouble for that.
Oh, God, yeah. There was a long investigation. It was actually fascinating at the time because every couple of days the investigation team gave a really detailed briefing about what they had discovered. So it was, for nerds like me, it was kind of fascinating. Anyway, moving along, there's these things called hypergolic fuels.
I've been like that. I think sometimes when I eat prawns, I feel very hypergolic.
So these are like ridiculously reactive chemicals. So again, we're talking about complex chemistry here. So you have some kind of complicated oxidizer and some kind of really complicated fuel, and as soon as you bring them into contact with each other, they just literally spontaneously ignite. They're not used for large rocket engines. Apart from anything else, the fuels are ridiculously toxic, so they're really difficult for anybody to handle. And, if you get a leak or anything, you're going to kill half the employees on the pad.
That wouldn't be good.
But the other thing about them is, of course, they're expensive to make. And what they have been used for is what's called maneuvering thrusters. So after a rocket gets into space, if you want to steer it, make it go left or right a bit or up or down or whatever, you need these small little rocket engines on the side of it that squirt out little jets of thrust in one direction or another.
Yeah.
And they have used these hypergolic fuels for those. Because they're reliable and simple, you just literally need to get the two of them into the same space and they'll ignite. So that's hypergolic fuels, but they're not really used very much. And the two other kinds of interesting rocket propulsion, thing called electric ion thrusters. So these are not powerful enough to launch a rocket off of the surface of the Earth, but they use very little fuel. What it is they take a gas, typically xenon, and they're able to set up two electric fields at opposite ends of the engine, and with an opposite charge, so there's negative at one end, positive at the other, and the static electricity charge in the chamber accelerates these xenon gas ions out the back, and you get a small bit of thrust. So you might say, why would you bother with a rocket engine that only pushes a small bit, doesn't have big thrust? And the thing is, once you're in space, if you want your satellite to be able to maneuver a little bit, maybe it's drifted slightly out of position and you want to get it to go back into position, you don't need to push very hard.
You could use like a leaf blower.
You could if there was air in space for the leaf blower to push.
If you leaf blower with xenon gas in it.
So the good thing about these ion thrusters is they operate at very low thrust, but they use very little fuel. So you could run one for days With, you could carry a few liters of xenon gas compressed, and you could run one of these thrusters for days just based on. So they're grand for like long term slow acceleration or maneuvering. And finally, my favorite type of alternate propulsion that thankfully nobody has actually tried yet, but it's a staple in science fiction novels, and it is theoretically possible. Somebody tells us, and that is nuclear bomb propulsion. So
they don't even go with the fusion or the fission. They're just going straight to the bomb. It's a bomb. It's a nuclear bomb. It's not about making energy.
No, it's not. It's not about making energy. But it is about making energy, but not electricity. So the basic idea is that you build this massive big spaceship, and once you couldn't use this to get a spacecraft off the ground on Earth into space, because you would destroy the ground underneath the spacecraft and everything within a 20-mile radius. But
Cape Canaveral would be
the idea is that
toast.
you would build this massive spaceship in orbit. So you would send it up in pieces using ordinary rockets. You'd build it in orbit around Earth, and then when you're ready to go off to Andromeda or wherever the hell you're going, there would be at the bottom of it this massive thick metal plate that might be 100 or 200 meters thick and much wider than that. There'd be a little hatch in the middle of it somewhere where you would chuck out a nuclear bomb, close the hatch quickly, the bomb explodes and pushes against this metal plate and pushes the ship forward really quickly. And then a few minutes later, you throw another one out the hatch and you explode it. And you just basically keep exploding nuclear bombs behind your ship to push you forward.
But would you not just keep going even after the first one? Do you have to
you would, but if you want to go somewhere really far, remember, space is absolutely enormous. So if you want to reach really high speeds, the amount of force produced by a nuclear bomb is far in excess of what an ordinary rocket engine produces. So you're going to keep accelerating yourself faster, because that's the only way you're going to get away to, say, another solar system. That's like our nearest solar system is, I believe, 4 light years away. Somebody's going to correct me on that, but I think it's 4 light years. So that means that it would take light 4 years to get there.
Yes.
So that's an enormous, like the speed of light is an absolutely enormous speed, which chances are we'll never be able to accelerate any vehicle anywhere near the speed of light. But even if you wanted to get to a quarter of the speed of light, so you could get there in 16 years, for example, the only way to do it would be something like this nuclear bomb propulsion that would accelerate you up to those massive speeds. And then the problem is, when you get there, how do you slow down?
Well, I mean, it's not going to keep me awake at night, but I'm sure somebody is thinking about it. But it's just the idea that, like, the best theoretical answer we have to traveling through space is to lob nuclear bombs out behind the ship whenever we need to speed up. I mean, is that it? Is that where we're at?
But it does have a fringe benefit in that, at the moment we have our military people have thousands of these nuclear bombs in stock, and at least if we could persuade them to send them off into space, there'd be less of a risk that they're going to blow up us with them.
Well, no, I wouldn't mind just shooting them into, just let them go, like, not set them off, just send them into space, let them drift
and let some
gently.
aliens find them and set them off.
Shoot them at the sun.
Oh no, we want the sun. We don't really want to blow that up either.
I don't think we do capacity to blow up the sun, though. Would we?
I don't know. I mean, if we put a lot of nuclear bombs in one part of the sun, would we damage it enough?
Would we push it off course?
I don't know.
Yeah.
Anyway, let's not explore that one.
Yes, let's just dwell on that. I think that could be another episode.
Perhaps it could. Let's get back to cryogenic fuels, because
I just couldn't wait.
They're the most common ones. The cold. So that's, to recap, that's gases that have been liquefied by making them really cold. But that, of course, brings some challenges. Of course, as I said,
gloves.
The reason
everybody has to wear gloves.
Everybody has to wear awfully thick gloves. As I said, the reason why you're doing it is, of course, it's very energy dense. So you get the most vigorous burning in your rocket engine. They only remain liquid if you keep them really cold. So in the case of liquid oxygen, you're talking about minus 185, and for most of the other fuels, the cryogenic fuels, is similar. So the tanks have got to be able to handle something called off-gassing.
Oh, I've been there. I've been blamed for that sometimes. I've been accused of off-gassing in very social situations.
Yeah. I know, and the cinema is like the worst place of all. Because you're doing your best to look around and say, who did that?
Yeah. I'm getting out of this lift immediately.
Knowing damn well you did it yourself. Anyway, the thing is, right, at the tank of cryogenic fuel of liquefied oxygen or whatever it is. At the top, there's going to be a small gap at the top of where the liquid stops and the gas starts. And that's a little warmer than the liquid part. So what's essentially happening is the surface of that liquid is constantly boiling because of the fact that that gas space at the top of the tank is a little warmer. And as a result, what was liquid is becoming gas at the top in that space. And the pressure of the gas in there is rising all the time because more of the liquid is gradually turning into the gas. And if you don't deal with that, essentially your tank is going to burst from that increase in gas pressure at the top of the liquid.
So you shouldn't. Like the message is that you shouldn't hold it in.
Yeah,
you shouldn't keep it
No.
in. You should always let it go.
Let it
go. Okay, let it go.
So that's the first problem they have to deal with. They have to have vents in the fuel tanks. And if you see a rocket sitting on the launch pad about to launch, you will usually see some kind of gases drifting away from it, from little valves in the side of it. And that's because they're venting the gas out of the fuel tanks to stop the fuel tanks from bursting. So that's the first thing. Then the next thing you've got to talk about is all that fuel and oxidizer, it's going to be travelling through pipes and valves and pumps and various other pieces of plumbing that are part of the rocket. And all of those have got to be able to handle this extreme cold. So, most materials become brittle when you make them cold like that. So if you subject them to a lot of stress, a lot of physical stress, they're likely to crack. It's actually a bit like it's a bit like people. Yeah, a lot of stress and they're going to crack. And then often these materials, when they get cold, will contract. They'll get slightly smaller. So if you've got, say, two pipes that are joined together, the gap, the seal between the two pipes mightn't seal awfully well anymore if the pipes have shrunk a bit because they're so cold. And then at the other end of it, when you light the engine, the pipes that are down near the engine are going to suddenly get really hot, because the engine gets awfully hot. So it's really difficult to make pipes and valves and pumps and stuff that can handle both things, that can handle the cold and the heat. Then you need, obviously, your tanks and your pipes and all that have to be insulated to try and keep the liquid from getting too hot. You want it to stay as liquid, not turn back into gas. And another insidious problem is it's difficult to remove every last bit of moisture that's dissolved into the fuel. And when you make the fuel that cold, that moisture that's in it will decide it wants to turn into ice. So you can end up with bits of slush floating around in your fuel, and suddenly the pumps start running, sucking fuel out of the tanks, and that slush gets sucked into the pipes, and then it blocks the valves or it blocks the pipes. So there's all these problems that have to be dealt with. So
I'm reading completely different into this, but yes, rocketry. We're talking about rocketry.
So what's your insight into that?
Well, I mean, it sounds like my last medical examination.
And did they find any slush in the pipes?
Well, they didn't want to tell me.
But yeah, so it is rocket science.
It is actually rocket science.
So I suppose that's the fuels, but of course there's other extreme engineering challenges involved in rocket engines. So
I don't believe it. I don't believe that. Surely it gets easier after this.
No, we're only getting started. So there's like the combustion chamber. So essentially you've got like a bell-shaped thing at the bottom of the rocket that we're all familiar with seeing, kind of a cone-shaped thing that sticks out of the bottom of the rocket. So at the top of that cone is the combustion chamber where all the burning takes place inside. And like the metal, the heat of the temperature, you remember we're using really energy dense fuels and they're burning really vigorously. So the temperature in there is way above what's necessary to melt that metal. So in seconds, your rocket engine could be reduced to a pile of molten metal. And so to deal with that, they have a real innovative method of dealing with it. I don't know if you've ever noticed, if you look closely at some rocket engines, you'll see these.
I think I can say no already to this question. I think
you
I can
have
already
not looked closely at rocket engines.
I think I can I'll jump ahead and say no.
I'll send you a couple of 100 pictures on WhatsApp for you to study. But so you might notice these circular ridges going around the outside of the rocket bell. And what's actually going on there is they are pumping the cryogenic fuel through the little pipes that are running around the outside of the rocket bell to cool it down, to stop it from melting. So they're actually using the cold fuel as a coolant to cool the body of the rocket engine to stop it from melting. It's really
so essentially, if they didn't do that, then there'd be
Oh,
the cone to be gone.
They'd melt. Yeah, they'd literally melt into liquid. Yeah, and the engine would basically come apart, and you'd have a very big explosion then. So that's one challenge. Then of course there's the pure physical pressure. I mean the when the rocket engine starts firing a lot of hot stuff out the back, and Mr. Newton's law comes into effect, there's a huge amount of forward pressure coming from the engine on the structure that's holding it in place, and all the pipes that are connected to it from the fuel tanks and so on. So they've all got to be able to cope with that pressure. Typically, you get a lot of strong vibration because the burning is not perfectly smooth, so the engines are vibrating, shaking violently, and so that can result in causing cracks to the support structure that's holding the engine in place, or the pipes or whatever. And we can probably do a whole episode on rocket fuel pumps because they are.
No, let's not do that.
They are the most incredible pumps you have ever heard of. They have to pump huge quantities of fuel to satisfy the appetite of the rocket engine. I mean, the Saturn V moon rocket, that was the first stage of that. We'll talk about stages in a minute, of the Saturn V moon rocket, which is the rocket that brought men to the moon at the end of the 1960s, the start of the 70s. It burned at takeoff, it burned 12,000 litres per second. Imagine the kind of pumps you need to pump 12,000 litres of fuel every second.
I can't actually. I can't.
Yeah.
My imagination stops short of that.
Yeah. So like they have to run at massive high speed, and when you run any pump at high speed, you've got a risk of cavitation, which we mentioned in another podcast is essentially little gas bubbles forming and damaging your pump blades when they collapse again, and it's due to the high speed agitation of a liquid. So cavitation is a risk, and then because they're running so fast and there's freezing cold fuel going through them, you need bearings that, you know, the shafts of that the rocket blades or that the pump blades are mounted on have got to have bearings to allow them rotate, and those bearings have to be able to cope with high speed and extreme cold. So like the engineering of those pumps is something else. Then you're talking about, I mentioned earlier on, cryogenic fuels is hard to get pipes to seal because the pipes are expanding and contracting and there's all the vibration going on. And then a problem which is really only become a problem in recent years when SpaceX have started reusing some of their rockets, and something we're going to discuss in more detail later on, is sloshing of fuel. So if you say you've used up 3/4 of your fuel and you turn off your engine, and now you want to turn the rocket around and make it go in a different direction, and then you want to turn on your engine again, by the act of turning your rocket around might cause the fuel to slosh up to the other end of the tank, and suddenly your pumps are sucking air, sucking gas. They're not sucking liquid fuel anymore out of the tank. So there's all those problems have to be dealt with. Then you've got, it's very easy to have uneven, like if there's turbulence in the combustion chamber where bursts of fuel or bursts of oxidizer are coming in blobs, you can get this uneven combustion, and that can cause the engine to literally explode. So you need to have your combustion nice and smooth. So there's all these problems that have to be dealt with. And finally, oh thank God, we're going to come to the sound wave produced by the launch of a rocket.
Right.
Like the noise is so loud and so intense, you know, confined into a small area, that those pressure waves in the air that are the sound, they actually cause physical damage to the launch pad, to the rocket. They hit the ground underneath the rocket, and they can reflect back up and damage the mechanism of the rocket engines, the fuel tanks. Like, it's another huge problem that has to be dealt with. And often sometimes you see when they're launching a rocket, you see this massive spray of water turns on in the last few seconds before they light the engine, and that water is to absorb sound. So that water is to stop the sound wave from actually causing damage. So there's like
they're shooting water at sound waves.
Yeah.
You know what just disgusts me about this whole situation? Like, they've looked at all of these engineering problems, and they have found solutions.
Yeah.
Like, through years of graft and hard work and study and understanding physics and chemistry and the sciences and engineering. And at the same time, when I bring the car into the mechanic, he can't find out what is wrong without it costing like 10 grand. Like, I don't understand. Like, they can do all these things, and surely at the combustion engine and all the bits in the car, surely can it's like playing with Lego for people now, for these guys.
Yeah, I know. I mean, we both of us know somebody whose car has spent 3 months in a garage until they figured out what was wrong with it. And you would think with all modern electronics and the fact that every car engine has about 3 computers in it now, that they could just figure out that stuff in 10 minutes with a probe of some kind. We're getting back to probes again.
Yeah, here we go. Back to the probes.
Yeah, and I'm sure it has absolutely nothing to do with the desire of the garages to maximise the amount of money they make from repairs and
Just
diagnostics.
send all the mechanics to NASA for 6 months. And
Actually,
they come
preferably put them on top of a rocket.
No, we need them. No, I love mechanics. Don't listen to them.
So, stages. We spoke about stages.
Oh, you should be on the
earlier
stage or in prison. Special wing in the prison for you.
I don't know. I mean, prison life, I just don't know if I could cope with that.
Well, you'd have a lot of time to read.
I suppose I would, yeah. And I could teach all my fellow inmates how to make rockets.
Do like workshop on ballistic trajectories. I'm sure the prison authorities did like that.
I'd say some of the inmates might be familiar with ballistic trajectories. Anyway, multiple stages. So most modern rockets have what they call multiple stages. What that means is actually it's 2 or 3 rockets piled up on top of each other. So the one at the bottom lights up first and gets you away from the Earth, and after a while that one has used up all its fuel, so you throw it away and you turn on the second one in the stack, and it runs for a while, and then it uses up all its fuel, and if you have another one, then you throw away the second one and you light up the third one, and that's called staging. There's first stage would be the lowest one, second stage, third stage, etc. So most rockets have at least 2 stages, some have 3. But
like all together now.
Oh yeah, like Lollapalooza, or what was the one? Glastonbury in England. Yeah,
There's more than 3 stages.
Yeah. So what's the point in doing that? Well, for starters, you can reduce the amount of weight that you're having to lift. So by burning all the fuel for the first stage and then throwing the empty fuel tanks and the engines for that first stage away, you're saving all that weight. So how much might you be saving? If we go back to our friend, the Saturn V rocket that brought people to the moon, the empty first stage was 130 metric tons. So that was 130 tons they did not have to bring any further with them. So, and the other thing is that you need most of your power earlier on in the flight to get off Earth and to build up your initial speed. So later on, you can get by with less power once you've reached a certain amount of speed and you've gotten above the densest part of our atmosphere. So you can throw away your big engines, throw away your big fuel tanks, and just turn on smaller engines, and you now have less weight to lift. And the result of it all is that you can get more stuff into orbit. You can get whatever your payload is, be it a satellite or a capsule with people in it, you can get bigger ones into orbit by using this multi-stage method. And
they're still doing so. That's the standard for
that
currently.
Is the standard, because if the theoretical other way of doing it is single stage to orbit, or SSTO it's called, and the thing is,
wow, you're obsessed. You're obsessed. There's about 8 people in Ireland who know what that acronym means.
I'll be asking you tomorrow what that is, and I'm sure you'll remember. Anyway, the physics of the whole thing, because of the strength of Earth's gravity and the amount of power you need to get away from that, the physics of using a single stage rocket means that you have this enormous rocket that might be 60 or 70 meters high, and eventually you are able to put something into space that's the size of a dinner plate, So if you want to get a usable, decent amount of stuff into space, you've got to use multiple stages, because just the physics mean that one stage is just not powerful enough.
Yeah, I suppose it's just good to know that if you're having a dinner party like on the space station and you're just one plate short, at least they don't have to use multi-stage rockets to get it up there.
Send up the plate. Send up the orbital plate. So there's different kinds of. What is your rocket going to do when it gets up into space, when it gets away from Earth? There's different.
I can think of several things, but I'm going to remain quiet on those.
Ideally, it's not going to blow up. Although
Yes.
some of the more recent SpaceX ones have been blowing up. I'm sure they'll solve that problem soon. So there's 3 basic things your rocket might do when it gets into space. We'll talk about the biggest one first. That's escape velocity. That's where you actually want to get away from Earth altogether and go off to deep space. You want to completely leave Earth's gravity behind. So you're not going to get pulled back down by Earth's gravity after you switch off your engines. And escape velocity is 40,000 kilometers, slightly more than 40,000 kilometers an hour.
Regardless what size you are.
Yeah. It's just to do with the amount of strength of the gravity of the Earth. So that's used rarely enough. Obviously, if people are going to the moon, they need to go to escape velocity, or if they're going to Mars or the outer solar system. But an awful lot of the rockets we launch are on an orbital trajectory. And what that means is you don't go fast enough to get away from the Earth, but as soon as you launch your rocket, you point it sideways, like more parallel to the surface of the Earth, and what happens is you reach a certain speed where you begin falling. You turn off your engines. It's not escape velocity. It's typically half of that, say a little bit more than 20,000 kilometers an hour. You switch off your engines and you start falling back towards Earth. But because you're going sideways, you miss the Earth. You fall down the side of it.
Okay, this is hurting my head now.
Yeah.
So the rockets are falling, but hitting the Earth.
Yeah. So they just go down the side and keep falling and keep missing it. That's what orbit is.
But then, so if they fall and then they fall in a different direction, or is it just because the Earth is spinning that they just are falling in one direction?
Remember, you pointed your rocket sideways,
yeah.
right? And you then accelerated like mad.
Yeah.
So you're going sideways at a huge speed, right? But at the same time, you're also falling downwards. So if you like, you're going diagonally.
Right.
Your initial sideways direction, then you pull that down a bit from the gravity of the Earth. But you don't pull it down far enough to actually hit the surface of the Earth. Instead, you miss the Earth and you keep falling around it.
But but you keep falling after the engines are switched off.
Yes. Oh, yeah. After the engines are switched off, and that's so we put up satellites or the space station, all those things, thousands of things that are in orbit, are doing that constantly.
But where's the Facebook page called Chicken Licking? All the satellites are falling. That's that should be. All the satellites are currently, right now, what you're saying is all the satellites that are in the sky are falling.
They're falling, but they're all going to miss us. They're going to miss
falling. That's all I'm interested in. They are falling. They're falling towards us for a little brief span of time and then just shoot by and miss us. This is now.
That's what an orbital trajectory is. And depending on how high you want to go away from the Earth. So you could have a low orbit. That's, I suppose, the lowest orbit might be in the region of 150 kilometers away from the surface. But then some of the likes of the GPS satellites are thousands of kilometers away. So the speed you have to go at will differ depending on how far away from the Earth you want to be in orbit. But the principle is the same. You're going sideways fast enough that when you start falling back towards Earth, you miss the Earth and you fall down the side of the Earth, and you just keep doing that.
But you don't need to use any more fuel. You don't have to switch anything else. So once you hit that orbital velocity, and then
you're going the right direction,
turn your engines off, that just goes forever.
Except the lower down ones, right. There's very tenuous wisps of atmosphere in the where they're orbiting, and that gradually begins to slow them down. Like months later, they might actually fall back into the atmosphere because they have slowed down enough.
I thought you were going to say many decades later they might fall down, but no, a couple of months after they put them up there.
Well, it depends on how high they started up. It could be decades. But for example, the space station, which has been in orbit there for about 15 or 20 years, they have to boost up the speed of that. They have they send up rockets with.
So the space station is falling now. It's not just the satellites.
Everything that's in orbit is falling. But they send up rockets with supplies for the astronauts or with new astronaut crews. And they use the engines of those rockets periodically to speed up the space station a little bit so it doesn't fall.
Give it a nudge.
Yeah, to speed it back up because it's getting dragged a little bit by the tenuous atmosphere. So the other kind of trajectory, which we spoke briefly about earlier, is ballistic. So that's where you don't go fast enough for escape velocity, and you don't go sideways enough for orbit. So you're kind of going not quite straight up, but quite high up. So you go up into space, then you turn off your engine and you start falling back down in an arc.
Right.
That's typically used by missiles. So
are there any good uses for this one, though? Are there any happy uses for this? Or is it just purely to strike fear into the hearts of children?
Enough, you mentioned Katy Perry's little adventure with Jeff Bezos' space company. the other day, and that they use a ballistic trajectory. So they launched like essentially they're bringing space tourists for a very brief jaunt into space. So they literally barely go out of the edge of the atmosphere on a ballistic trajectory, and then they fall back down again and land on the Earth. So they're only up there for a few minutes. But no, mostly the thing about ballistic trajectory for rockets is when it's coming back down, it's by the time it gets into the atmosphere, it's going at enormous speed. It's coming more or less straight down at you. It's really hard to shoot that down. Like the speed that it comes down at means that most anti-aircraft or defense missile systems can't target it, because where you thought it was going to be, it's now 50 yards further down in a matter of a second, So that's what ballistic trajectories are.
So ballistic trajectories essentially are evil.
Yeah.
Not because of the missiles, just for letting Katy Perry into space.
You realise now we've lost half our listenership because you're slagging off poor old Katy.
I'm not 100% sure the old Katy Perry listenership is like tuning in to Enough with the Science. I'm not 100% sure.
At this point, I have to step in. We're going to stop insulting people and move along. Right, let's talk about everybody's favourite SpaceX rocket company. We're going to forget about
your favourite.
We're going to forget about the elephant in the room of a certain individual who's in charge of that company.
Yeah, we'll focus on the science.
Anyway, they have developed a unique ability to land the first stage of their rockets and reuse them. Nobody else has been able to do this. SpaceX have been doing it now for several years. Every other rocket company or even government that's launching rockets, the first stage of the rocket is allowed to dump into the sea and is demolished basically when they throw it away. Whereas SpaceX have figured out, after a lot of trial and error and a lot of explosions where their rockets didn't land successfully, what happens is, so the first and second stage, the bottom half of the rocket separates from the top half. And then after a gap is allowed to, builds up between the two halves, it flips itself over. It uses tiny little rocket engines to thrusters, they're called, to flip itself the other direction. And then it lights its engines again and it starts heading back the way it came. When it's getting close to the landing area, it essentially falls back down. So it has reduced its speed a bit by going backwards. And it essentially falls back down and uses a really precise set of steering fins and little jets to glide it back to the landing pad. So the real magic here is the ability to navigate something that's essentially a flying skyscraper falling through the atmosphere with no wings or anything, just these tiny little fins and jets, to be able to use those so precisely with computers. This is all controlled by computers. To let it glide back down to the exact right place for the landing pad, and
this saves gazillions of.
Yeah, because they then they can reuse it, so they're throwing it away.
Yeah.
So it's much cheaper for them. They sell launch services. So companies that don't, or countries that don't have their own, or indeed companies that don't have their own rocket launching abilities, they can pay SpaceX to launch their stuff into space. But the really hairy part of this procedure is when the rocket is landing, the engines are too powerful to actually hover, right? So they've got to light the engine just above the ground. Now, by just above, we're talking about maybe 50 meters above the ground at exactly the right time, so that just when the rocket falls to be level with the ground, it's at zero speed. Because if they light it a couple of seconds too early, it's going to be at zero speed, like maybe 10 meters above the ground, then it's going to start going up again.
Right.
And if they light the thing a second or two too late, it's not going to be at zero speed when it hits the ground, and you know what happens then.
It's going to crash.
Yeah, it's going to explode into pieces. So that is like, it's really cool to watch how they just finely tune that engine to lighting time to get it to just get to zero speed as it draws level with the ground. But essentially the benefit of this, and it's amazing, they've been doing it for several years now and nobody else has managed to repeat that process. Jeff Bezos, we mentioned him a moment ago, he has his Blue Origin space company. They're trying to do it. They've only tried once with their new rocket, which is called New Glenn, and it crashed. They didn't succeed on the first attempt. But it makes SpaceX much cheaper than everybody else for launching stuff into orbit, because they're reusing a single booster. They call it the first stage. Another name for the first stage is a booster. A single booster, they've used some of them up to 15 times. So instead of manufacturing 15 new boosters, they used the same one, and so it's much cheaper to no, they're absolutely killing the launch market at the moment because nobody else can compete with them. So much so that they're launching about 2 rockets a week every week. SpaceX now
to bring stuff into space.
Yeah.
Who knew the market was so big? Who is it's like we want our own satellites? This is very Bond
a
bad
lot
guy
of it
stuff.
is their own. They have this thing called Starlink, their internet system,
Yeah.
and they have thousands of those satellites up there, and so a lot of those launches are for their own purposes. And finally,
now you didn't say nefarious there. I'm not saying nefarious either because we don't get sued. But just there's a word nefarious.
I need to look that one up in the dictionary. I don't like using
nefarious
words I don't
purposes.
Is that something to do with fairies? Anyway, we're going to talk about one more thing, which is also a SpaceX topic, and that is they're developing this new Starship system, and some people call it a big leap forward in rocket capabilities, and there's a few reasons for that. First of all, it's by far the biggest and most powerful rocket that anybody has ever built, which that means that it can either put really big things into space or lots of people.
Or really big people.
Yeah, small amount of big people or a huge amount of small people. But yeah, this thing is enormous. It's 123 meters tall, when it's standing on the launch pad. And that's 26 meters higher than Big Ben in London. And it's also wider. It's about 9 meters wide, I think. So it's much wider than other rockets as well. So it can carry a hell of a lot more fuel. It's got, the first stage has 33 engines. And even that in itself is an engineering miracle because do you remember the space race between the Americans and the Soviets to see
who could forget
to see who could get to the moon first? The reason the Soviets failed was their rocket, the N1, I think it had 26 or 27 engines, and they could not sort out the vibration problems. So when all those engines were running together, all the vibration harmonics in the vehicle just broke it up. So, for SpaceX to even get a rocket with 33 engines on it to work is a miracle in its own right. But the second stage, then the upper half of it has 6. One of the key innovations, apart from the sheer size of it, is they're going to try and make the second stage reusable as well. So nobody, including SpaceX up till now, has managed to soft land the second stage of a rocket and reuse it. And the way they're doing it is really cool. They're actually gliding it down. It has wings, this thing, and the second stage, and they're gliding it down sideways. And at the last moment, just before it's going to land, they flip,
or crash.
Or crash. Well, it has crashed. There's been some spectacular crashes. They've test launched it about 10 times now, but at the last minute they just flip it upright and land it on its base. It's really cool. So if they can reuse both the first stage and the second stage, it means the cost of getting stuff into orbit per kilogram is even much cheaper again than it is with.
So it would be cheaper, say, to get rid of the body of a co-host in space.
Yeah, but then this podcast would become a monologue, and people have only a certain amount of tolerance for that kind of thing. Another interesting, it's still in the test phase, and they've got a lot of it to work. They've successfully landed the first stage a few times now. In fact, they use these really cool robot arms to grab it out of the sky, so they don't let it go all the way to the ground. They have these massive robot arms that grab it while it's on the way down. But the second stage they've had a problem with. That's been blown up a couple of times in some of their test flights. But they have actually got it down to sea level and just softly dropped it into the sea a couple of times. So they're nearly there with getting the second stage reused as well. So a lot of the scientific exploration robots that we send to Mars or Saturn or Jupiter or whatever, they're extremely weight constrained because the rockets we have, the traditional rockets we have, if I can use that word with rockets, are so they're only capable of launching small amounts of weight into escape velocity away from Earth. So that means that the scientific instruments on those robots are really, really weight constrained, and they can only put really lightweight, simple instruments.
A dinner plate.
Yeah, on those robots.
Yeah.
This thing will allow them will remove those constraints, and we'll be able to send big, heavy robots to other planets with lots of sophisticated scientific instruments on them.
You're saying this with the glee of someone who thinks it's a good thing.
Let the robot invasion commence. Some other things they're going to do with it. They're using methane, cryogenic methane, as the fuel, and they believe it should be possible to manufacture that on the moon or on Mars from locally sourced materials that are already there. So it brings the option of actually refueling the vehicle and using it to fly back to Earth from the moon or Mars or wherever. They're also looking at in space refueling, where they like launch one of them and it's in orbit, and then they launch a second one, only use half the fuel in that one, and fill up the first one from the second one. Again, it adds extra flexibility. So this is like
this is where we're going. This is future.
It's a big leap forward. Yeah, if they can get it to work. I mean, they have massive factory. Like they have a production line for these things. They're building, like they have dozens of them being built at any one time. So if they can get them to work, it's going to be a new exciting age in space exploration. And I think
I mean, you've really hidden your love of rocketry under a bushel for this podcast. I don't think people really, like, I'm staring across at the gleeful eyes of a madman when he's talking about rocketry.
You can pick the next topic. You can be completely self-indulgent about the next topic for next.
No, that was very I don't think I could have come up with a more interesting topic, Sen. That was brilliant and an awful amount of information, but I do think after that amount of information, we do have to say enough with the science for another episode.
Yeah, we don't have any rocketry limericks, do we?
We have no rocketry limericks because I've lost the poetic urge.
The limerick AI is on holidays this week.
Yes, absolutely.
Yeah. Anyway, that is enough with the science. I'm Senan, and until the next time.
Catch you the next time. Take it easy.